of the signal path. It's been so long since I've made a video, and I've gotten so many messages from you guys asking if everything's okay, and I really appreciate your concern, but everything's okay. And I posted on Twitter that I've moved to a new place and I haven't had a chance to set up the lab. There's so much work to do when you move into a new house. As you can imagine, just moving the lab itself was quite a hassle. And it's not ready yet, but I'm going to finish the basement, put the lab in there, and I have quite ambitious plans for so many cool experiments that we can do in the future once everything's settled down. But in the meanwhile, it doesn't stop us from doing a few things here and there. I have some reviews and a bunch of other things that I want to do for you. So first thing first, I'm going to do a Q&A. I've never done a Q&A before, so every question that you may have, you can post on this video, and I will grab a whole bunch of them and do a 30-minute episode answering your questions. And they can be about careers, electronics, or any other question you may have. But for the purposes of this video, we're going to look at some high-power microwave amplifiers. There's a bunch of boards that I found while I was moving that was in a couple of the boxes, and I thought I'll show you how they work and how they're designed, and this should be pretty interesting. And then from there on, I have a few other things to show you. So let's get started. And well, check out what I have here. I have a bunch of boards and a really neat antenna and diplexer module that I want to show you, and these are parts of a WCDMA LTE base station type of application. Exactly not sure from where they came from, but just looking at it, you can tell that these are definitely used for cellular applications. And there's two different boards here, and despite the fact that they kind of look similar, they do quite different things. So we're going to go through that and take a look and see how they work. And I want to talk a little bit about power amplifiers and power combining methods and the different architectures power amplifiers can have, because these guys can put tens and tens of watts out, up to 100, 200 watts of power. So pretty interesting to see how they work. And then this guy, I'm gonna have to save this for a different video because I want to actually do a measurement on it, and I don't have my equipment here. But this is a really neat dual polarization antenna, this is a patch antenna. This is a coupled patch at the top, and you can see a couple of traces at the bottom there where the main antenna module is. And at the bottom, there is a diplexer, and this diplexer has two polarizations and separates the TX and RX for both of them. So a really cool system that I want to show you later on, and we can take it apart and take a look at it. But for now, let's focus on the power amplifiers themselves, because there's a lot to learn from here. So let's start with this one. Alright, and here is our first board, and check out how beautiful it is. This classic microwave design. If you've done any of these, it would immediately jump out of the page of exactly what is going on here. So it's very interesting. So let's follow up and see if we can figure out what's going on. Well, the first thing is that we already know this is a power amplifier, so that kind of helps. And we want to follow the signal. I don't have the schematic or anything for it, so we're going to have to do a bit of a reverse engineering. And you can see my cat's head shadow on the board there. So now if we go ahead and take a look at find our first initial point of our RF signal. Now that's going to be right over here, because this is our first amplifier stage. Now this is a preamplifier, just providing sufficient power to be able to saturate the two amplifiers that follow. Because if you don't do that, then you're going to have to put so much power in here, because these guys don't have a lot of gain. So this preamplifier is going to blow up the signal just big enough to drive these guys. Now this is its input right over here, so we can draw on this board and see where the signal enters, but that of course then ends abruptly over here, and that's because its placement is a little bit inconvenient for how this board must have been placed in the big system. So if you follow the ground stitching on both sides, you can see the transmission line, the microstrip line, that was being carried away from this pointer circuit all the way up to this connector over here. So they have buried that transmission line in between and multiple layers to protect it for any noise coupling, and really ground stitching around it to make sure it's nice and quiet, because you don't want to couple any signal through here. In fact, if you're not careful and you couple signal from here to here, you got yourself a loop and an oscillator, which would be quite bad. So they have to make sure that this is really well isolated, and they had no choice because they needed to put the connector here. And this connector has all these pins, which of course are for DC, as well as some control signals. So we can follow that. I can draw over here. There is our signal coming in. Oh, that's very squiggly. Over there, and it goes in, and now it comes out of here, and there's a somewhat amplified signal as our initial point. And if you look on the left and the right of that, you see two little inductors and a couple of passives and capacitors around it, and that's the bias T network to provide biasing for this device over here, because they have to bias it directly through the output transistor so that you can have VDD, and then it's isolated at the RF frequency from the choke that's there. So that's pretty straightforward, and the signal comes over here, and they have an interesting little coupling mechanism built here, or perhaps the possibility to divert the signal out from here for some other purposes, but let's forget about that for a second. And then a signal comes in and reaches this little component here, and that component is a quadrature hybrid. And what it does is that it splits the signal between 0 degrees and 90 degrees with 3 dB less power on each port. The 3 dB less power is because, well, when you split power passively between two paths, you're going to lose 3 dB. That is not really lost, it's just split between the two paths. And then there's insertion loss on top of this. We'll take a look at the data sheet for that in a moment. So now we have a signal coming up here. Let's say that's a 0 degree signal, and the signal coming out of here, which is a 90 degree signal, and we can follow that signal, and you can see that it goes through some more passing, a bit more matching network, and then it enters this massive device over here, and the same path goes over here and up to this transistor. And then right over here, the component I just marked, that's a 50 ohm resistor that is connected to the isolated port of the quadrature hybrid, and we'll know why that is in a second as well. So now we have two signals which are split between 0 degrees, I can put 0 degrees here, and 90 degrees over here, that are going to between these two amplifiers. Now these two amplifiers are nothing more than a pair of LD MOS transistors. These are laterally diffused MOS transistors, and I'll show you why they use that as well. You see, you can just go so deep at every component I can talk about an hour about, but anyway, let's just try and see how much we can cover here. So we've got two LD MOS transistors, which are very high power devices. They can put out tens and tens of watts, and then the output of that comes over here and over here, and again you can see bias T's and bias network, and as well as the output matching network around the output of these devices. And if you look very carefully, somewhere around there you will find a point where the biasing of the transistor can be controlled with some of the microcontroller devices that are around. So the biasing must be controlled from the input. There it is, that's the resistor right over there. This is a bias control for this transistor, and this path right over here you can see is controlling the other transistor. That's how they change the biasing of these devices, and the output current, the DC current, is provided from this side. So we follow that again over here, and we can see that the signal jumps over this component and then goes back into another quadrature hybrid. And then the same as goes on this one, goes over here, goes down here, goes up there and there. And if you look at this, these are all length matched and so on. And it gets into this component, which is another quadrature hybrid. And then the output is finally taken this way towards this component. And I'll talk about that in a second as well. So, but why would anybody do this? Why would anybody split the signal between 0 and 90 degrees? Only then to combine them again between 0 and 90 degrees after another quadrature hybrid? Why would you use two extra components which are not only expensive, that are not solid state, and on top of that they have a little bit of insertion loss, so you will lose some signal through these as well. So why would you do this? Why not just combine them some other way? And I will explain that as well. So this architecture is called a balanced amplifier architecture. This is a power combining technique for combining the power between two amplifiers. So let's see what that looks like. So what I just explained is exactly this block diagram. It's almost identical. I'm putting it right on top of the board there. You can see the signal coming over here, and the signal split between 0 and 90 degrees goes through our two amplifiers, which were our LD MOS amplifiers, and then they're combined again in the hybrid in the opposite direction, and they combine in phase at the output. And here's a 50 ohm on the isolated port on the output, and a 50 ohm resistor on the isolation port of the input. Now the reason they do this is because they want to take advantage of the property of the quadrature hybrids to create an amplifier that not only does power combining, but also provides excellent input and output matching to the 50 ohm load that drives the input and the output. And this will eliminate the mismatches of the amplifier, so that looking from the outside port, which will be the antenna, you will see a very good signal match, so you will not have reflections here, and the pre-driver driving this amplifier is not going to see a mismatch. Now this is really important for power amplifiers because matching big devices to 50 ohm is quite difficult. So often the matching is either very narrow band or very poor for these big devices, so you have to have something to be able to provide a good VSWR at the both ports and the input and the output. And how does that work? Well, it's kind of like magic, but it really is quite straightforward when you think about it. So let's take a look and see what that looks like. So here's another diagram there that I borrowed from microwave website there. And here's our first amplifier, here's our second amplifier. So we are looking at it from the perspective of the input, but it applies exactly the same way to the perspective of the output as well. So here, this amplifier number 1, this amplifier number 2 have a reflection coefficient gamma 1 and gamma 2. So they are not perfect, they're not matched to 50 ohms, there is some reflection coefficient. And the signal comes in with a phase of 0 degrees, gets split through the quadrature hybrid. So now you have a signal arriving at the amplifier 1 that has 3 dB of loss, that's what the root 2 over 2 is, but still has 0 degree phase. And on the other side, you have exactly the same signal, 3 dB down, except this has a 90 degree phase. Now, if these two amplifiers are not matched to 50 ohms, they're going to reflect some power back. And that reflection is right over here. You can see the signal reflecting back. So now you have a gamma 1 coefficient reflecting the signal on both of these ports, but the phase is preserved. So the reflected signals are going to have the 0 and 90 degree phase. And if you follow from that, you will see that what's going to happen is that the signals are now going to go through the hybrid once again, and the two reflected powers at the input port are going to sum out of phase and cancel out, because the reflected waveform is one time experiencing 90 degrees and on the way back another 90 degrees, now it's 180 degrees, and 180 degrees is out of phase with the input, so that completely cancels itself out. So now you have absolutely no reflection coming out of the input port. But on the isolation port, they are going to be both at minus 90 degrees, and that means that they're going to add up in phase, so the reflected power due to the mismatch of amplifier 1 and 2 is absorbed ideally purely into the 50 ohm termination load of the isolation port of the quadrature hybrid, which is exactly what you want. So if this quadrature hybrid is going to absorb all your reflections, the input looking into here ideally is going to see a perfect 50 ohm, or as good as the quadrature hybrid is at least, and is not going to see any of the reflected signal. And that's the key, and that's the magic. You can see it here again, that the entire power here is absorbed with a 90 degree offset into the isolated ports 50 ohm. So this is why they do this, this quadrature hybrid at the input and output. And the output, you're going to see exactly the same thing, except you're looking at the output reflection coefficient of the amplifiers and not the input, which can even be worse than the input. So this is the magic of balanced amplifier design, and that's exactly what's happening over here. And you can see that any input reflection that these bounce back from here are going to come back through the hybrid, and as I explained, are going to dissipate in this resistor here. And same with the output, is going to have exactly the same property. So that's why we do this, and that's why they're using this balanced architecture. Now, why are they using LD MOS transistors, and what is the deal with this lateral diffusion transistor I was talking about? Well, I have a diagram for that as well. This is a very simplified and quite straightforward diagram of a laterally diffused MOS transistor. And unlike a typical MOS transistor, it has a lightly doped P diffusion region that sits in a lightly doped N diffusion region, which is not what a typical MOSFET looks like, and that's the reason they call it laterally diffused, is because of the property over here. Now, these lightly diffused P and N type regions are going to create a really wide depletion region, and a really wide depletion region means that you're going to have very high breakdown, and that's the key over here. And this allows you to be able to put huge voltage swings on the drain of this device and not completely break down the junctions that are traditionally created in a CMOS transistor, which is quite a bit lower power than an LD MOS device. And LD MOS devices have been used in base station forever. And this is all because of, to put it very simply, because of the improved diffusion width of the lightly doped regions created here. Now, there are disadvantages with this. The disadvantage is that this is not a very good device for very high frequency operation. So you don't really get LD MOS transistors operating at 100 gigahertz. But they are perfect for, you know, the few gigahertz or 900 megahertz that you would need for these low frequencies. But then processing has improved so much and the channel resistance has been reduced so much that they do have fairly good performance. But remember this, if you ever came across an LD MOS transistor, you know it has a much higher breakdown because of this unique property of the PNN extra diffusion layer, the lateral diffusion that they've created. And they create these with implantation and then annealing. They doesn't have to be typical diffusion, which is not very friendly for CMOS process. And this P plus that you see here creates a nice tight connection, good ohmic connection to this P regions. That's the bulk of the device itself, and they typically tie it with a source so that to get rid of the body effect. And this way your device has very few body effect. It's not actually a 4-terminal device anymore. It's going to be a 3-terminal device, although you could think of this one as being the bulk of the overall substrate, but this is the bulk of this particular transistor. Anyway, so that's the reason why we use LD MOS. And In fact, I do have a little data sheet for the LDMOS device as well. And here it is, just to give you an idea. This is one of the ones that are used in one of the two boards. I can't remember which one right now. You can see clearly it says this is designed for CDMA base station applications. And this particular one can operate at 2.1 gigahertz. And what is the output? It has 18 dB of power gain. You can get drain efficiency of 32%, which is not bad. 1 dB compression, 80 watts in CW, which is pretty big. So if you have two of them, ideally you can get twice as much power coming out. So really interesting, again, idea here that to use this. And you can see it says enhancement with lateral MOSFET. That's an LD MOS I was talking about. So that's another pretty cool little device. And unfortunately, I can't power them on, but maybe in a different video. And here's the data sheet for the quadrature hybrid I was talking about. And if you look at the quadrature hybrid, this one is for this board. So this frequency operation is from 800 to 1000 megahertz. Again, for GSM, WCDMA, LTE application. High power, low loss, which is exactly what you would want. And you can see its performance. It has about 23 dB of isolation, which is pretty good. And insertion loss of about 0.22 dB. It means that when you put in 0 dBm into one of the ports, you would expect to get minus 3 dBm and minus 3 dBm. Well, you're going to get a little bit more. You're going to get minus 3.22. And the rest of that loss is dissipated as heat inside the module due to resistive and so on, skin effects and properties such as that. And it has a fairly good VSWR, 1.15, which is pretty reasonable. And they're used two of these, one at the input and one at the output. And these guys are obviously this component and that component. So everything so far makes sense, and everything else that you see over here are nothing more than power distribution and obviously the monitoring power and DC blocks and DC-DC converters. Pretty straightforward stuff there. And then there is another component sitting at the output here. And what is the point of that? So the signal comes over here, enters this component, and then it comes out to this component. There is something missing here. Now if you've done any design like this, you would immediately know what this component is. So I'm going to give you a little quiz to figure it out until I show you another board that has it. So it's missing, something must have fallen out of this or broken off. And then there is a signal that's taken out from this port right here, and it goes over to some mysterious circuit over here. So what is the point of this and what is that? Well, that is nothing more than a directional coupler. And I've shown you directional couplers in my other videos before. And this particular directional coupler, I have the data sheet for it right here. And this one also works from 800 to 1000 megahertz as it makes sense. By the same company. And you can see that it has a 20 dB directional coupler, meaning that the signal coming into one of these ports goes through with almost no loss, because 20 dB of power is very little once you couple only 20 dB out. And the other port is going to get signal out which is 20 dB lower than the signal you're putting in. So is like taking a tiny bit of the power and stealing it away and doing something else with it. And the reason they do that is because these devices are sensitive to temperature, they're sensitive to biasing, they're sensitive to so many things, and you can even get into a thermal runaway, you can saturate them, you can damage them. There's so many problems that can arise if you don't monitor the output power. Now I want to monitor the output of this amplifier, how much power it's putting out, but I don't want to do that by stealing a whole bunch of power from it, because that would be a waste. If this guy is putting out, let's say 150 watts, I don't want to have to look at 150 watts of power. So instead I put it through a 20 dB directional coupler. I take only 20 dB lower power than from what is coming out, and I couple that little power and I monitor that. So here I can do envelope detection, power detection. I can detect how much power is coming out. Then I can use that in a system with a feedback to come back and adjust the biasing of these transistors to make sure they're operating at the highest efficiency with the correct output power. And this is my output power monitor port. And you can do even fancier things and do pre-distortion and all the other wonderful things that advanced modems can do by looking at the signal. So that's what the purpose of this directional coupler is to be able to do power leveling and adjustments and alignments and all the things you would need to do. And the component that's missing over here, I'm sure by now you have guessed, is actually an isolator. So I'll talk about that also in just a minute. And there is the other board that I want to show you, and this board is a little bit more complicated, and the reason it's a little bit more complicated is because it actually has both polarization amplifiers on it. So it has a two polarization amplifier system. So here's the first polarization amplifier, here's the second polarization amplifier, which would then go into that antenna that I showed you at the very, very beginning. So exactly the same scenario. You can see signal comes in, comes out of here. This is a filter and goes through here, but now things are going to start to look different. So we have some kind of a splitter here, definitely splitting the signal into two. That is no question. But then it goes through another pair of LDMOS transistors just like before, but then when they combine, they don't combine symmetrically like they did in the other board. You can see that this one comes over here and it goes out, so it has a very short path, but this one seems to have some kind of a transformer, transmission line that transforms the phase of the output there. And then there's a stop here, that's just a filter, forget about that. And then it goes out and it goes into this component here, which is another directional coupler. So that's the same as before. But then what is going on here? Why is the input and output of this don't look the same? It doesn't look like it's a balanced amplifier anymore. I don't have the datasheet or schematic or anything about it, so based on my observation, this is not the same as the other one. It's a little bit different. So what could that be? Well, I'll tell you about a whole different amplifier architecture, which this could be. And the other amplifier architecture that I think this one is a Doherty amplifier. And I have the block diagram of the Doherty amplifier here as well. Now the really neat thing about Doherty amplifier, aside from the fact that how it works, is that William Doherty actually worked at Bell Laboratories, which is where I work at. And he invented this architecture in 1937, and it's been used everywhere since then. And it's one of, it's a legacy essentially. And if you go and look at how many amazing ideas have come through Bell Labs during that era, it's incredible that so many brilliant minds actually worked in one place. I take pride in just going through the building each day and passing by the labs where these people have actually worked in. Anyway, so going forward with this, and we can take a look and see how the Doherty amplifier is different from the balanced amplifier we were looking at before. Now, in the balanced amplifier case, both of the amplifiers are operating in Class A or Class AB. Now, I've done a tutorial on Class A and Class B amplifiers, so you can go and watch that to understand the difference. But here, one of the amplifiers is in Class AB and the other one is in Class C. Now, Class C amplifiers don't have any power consumption when the input signal is small. So they only create an output when the input signal grows large enough to be within the conduction region of the transistors. So that means that this Class C amplifier doesn't produce any signal if the input is small, whereas Class AB here is going to provide the gain, it's going to produce an output amplification when the input signal is small. But when the input signal grows and the output of the Class AB amplifier is saturated and it can no longer produce an output, then Class C kicks in and is going to fill the gap and provide a little bit extra output power. So if you have your Class AB waveform that looks like this, and you can see the top and the bottom are flattened out because they're saturated, and then Class C only produces an output when the signal is at the extreme excursions, and you add them together, you get another output which is more linear, and it also has more output power. Now this is going to give you a lot more efficiency because the Class C only is working when there is the excursion. So that means that the overall amplifier not only can give you more output power, but it's going to give you that more output power at higher efficiency, which is exactly what you want, because the DC power consumption here is very critical. If you want to put that 100 watts, you don't want to burn 100, 200 watts just to do that. So you have to be able to provide output power with sufficient efficiency. So now, having said that, if the input of the Doherty amplifier is the same as the balanced amplifier, you got the same input, you got the same quadrature generator, same termination, which then protects you for input matching, which is even more important here because of the different classes. So everything is the same as a balanced amplifier here. And here they're also showing some harmonic rejection, some filtering, but we can ignore that. But now this signal is out of phase with this one, and you want to combine them in phase. So what they do is that they use a quarter wave impedance inverter or a transformer at the very output, so you're going to get 90 degrees, which then adds in phase with the original signal coming out. So you're now summing them in phase at the output, but you're not using a quadrature hybrid, you're using a quarter wavelength impedance transformer there. So, but then that means that the output impedance won't match 50 ohms anymore because of the fact that you're combining them in this way. So you're going to need an impedance transformer at the output, another matching network, to finally get yourself back to 50 ohms. So it has a disadvantage of this structure at the output, but a major advantage of being able to give you much more efficiency by doing this type of power combining. And that's what I think is going on here. And if you were to look at this, you can see what I believe is the quadrature transformer line being over here and the output being combining, and there's a stop here for matching. So this is your matching at the output, and then some more impedance matching line over here. Then it goes into the coupler just like before. And the output of the coupler here is taken to this port over here and out. So now you can see the component that was missing from the other board, and that's this one. This is an isolator. The reason it's an isolator is because the signal coming into it from port 1 can only go to port 2, and signal coming from port 2 will not go to port 1, will go to port 3. And port 3 here is this component here, which is a termination. This is an isolator is an extension of a circulator, a special case of a circulator. A circulator means that signal coming over here will always only travel, let's say, clockwise. So 1 can only go to 2, 2 can only to 3, 3 can only go to 1. They can never go the other way around. So in this case, output power going out goes directly through, but anything coming back from this way will not go back into the output amplifier, which is exactly what you want to do, because you don't want the large signal coming back from the other side to find its way back into the output of this amplifier and cause a whole bunch of problems. Instead, the output will go through 2 and it will go to 3 instead and get absorbed into the load of this isolator. This is also can be a circular, can also be called a duplexer, which is not the same as a diplexer. The thing that I showed you at the very beginning with the antenna, that was a diplexer based on microwave filters. A duplexer is in the same frequency. Totally different phenomenon. Now, because this is like a microwave magic in a way, I'm going to do a different video on it. But just know that it requires a ferrite core and a magnetic component in it. So this is not solid state and is huge and bulky and expensive to make because of the fact that it needs a ferrite as well as the magnetic component. And you can kind of guess how it works, because if you put a magnetic field around something, and because you have a particular phase of the signal coming in and a particular phase of the magnetic field, you can actually guide the signal in a different direction and don't allow it to come back against the field that's already there. And that's kind of a rough idea of how it works. But because of the fact that it's not solid state, they're quite expensive. And a lot of people, there is a lot of talk about making solid state duplexers and so on and on. Anyway, we can talk about it at a different time. But that's the whole purpose of this. And because this is a dual polarization system, you want to make sure the signal from the other polarization doesn't find its way back to the PA. And here you can see a whole bunch of other components. Again, bunch of DC-DC stuff over here. And you can see a bunch of components. I wanted to see what is going on. And as I said, because the biasing of all these devices has to be actively adjusted, you need to monitor a lot of signals, you need to monitor temperature, monitor DC power consumption, RF power coming out. You need some specialized components to do that. And in fact, this analog device over here does exactly that. And it's a pretty neat little component, and this is this block diagram. You can see that they've made this exactly for this kind of application. It has a whole bunch of 12-bit DACs which you can use to adjust the biasing network, the biasing of your amplifiers and transistors. It has temperature sensors. It has a 12-bit ADC with a MUX where you can put different temperature monitoring junctions around your circuit board to be able to monitor the temperature of different components. It has a whole bunch of other inputs. It has high side current sensing capability, which is great. It has a good 2.5 volt reference, which is used as a reference for the ADC and all the DACs as well. And there's a control logic block here which receives a digital signal and provides digital signal to all of these components over here, and a nice I2C interface for you to program it. So you have that one component monitoring a whole bunch of things, and you interface with it through the I2C and get all the biasing conditions set up. So that's a cool little component there, just to give you an idea of how they do that. And if you follow it very closely, you can again find out that right over here is where they adjust the biasing, and you can see that biasing goes over here into these blocks over here, and then clearly controlled by this one right here through these two resistors. You can see that this guy is controlling the biasing of this transistor. Same bias network over here which reaches also this device. Same with this guy for this device, this guy and that guy for this device. So you can see really clearly how they've laid this out so nicely and neatly. And here's a coupled power coming out. Massive DC connection here, as to be expected, because of the fact that this needs so much power, an absolute huge amount of power. And here's a control interface. And if I flip it over, you can see how the back, look how thick this is an aluminum backplate, and the back of this is just made for heat sinking. Look at the massive amount of area designated for putting thermal putties and so on, and getting the heat dissipated to the chassis of where this thing was supposed to be put inside. So really cool, neat little board And you can, I hope you learned a whole bunch of different things about how these things are built, and I'd love to hear what you guys thought about this. Again, sorry the lighting is not good, there's echo in the room, but my lab is not ready yet. But I promise you when it's ready, it's going to be amazing. We're going to do a lot of cool experiments. And just to remind you again, I'm going to do a Q&A, so post your questions on this video. And as soon as there is enough questions, I will do a special Q&A session for that. And I have a whole bunch of other cool things to show you. I have automated the heck out of my house. I want to show you how that automation works. A lot of cool things coming up. So I hope you're excited as I am. Until next time.